Okay, let's look at another example of half-life. And this one is a nuclear application. So we are looking at plutonium. So plutonium 238. The half-life is 24,100 years. Okay, so it takes a long time to decay, which is one of the reasons that we have trouble trying to decide what to do with nuclear waste, right? Because it's going to be radioactive and dangerous to people for so long. So it says 100 grams of the substance were left over from a nuclear reaction. How long would it take until there was less than 0.01 grams left of the plutonium? Okay, so first of all, we know that our basic equation is A of t is equal to A naught times e to the kt. And then we're going to plug the things in that we know so that we can solve to create a model for this equation. So first of all, there were 100 grams to begin with. And then we don't know the K, but they say that the half-life is 24,100 years. And that is the half-life. So that means if there were 100 grams to begin with, after that many years, there would be 50 grams, right? Half of it. So it looks like we're again going to be solving for K to find the rate, and then we will have an equation to use as a model. All right, so the first thing we want to do is divide both sides by 100. And therefore, 50 over 100 is a half, and that's equal to e to the K times 24,100. So now that the e is by itself, we can change to log form. So that's the ln of 1/2 is equal to K times 24,100. We're solving for K, so divide both sides by 24,100. So K is equal to the natural log of a half divided by 24,100. Okay, so basically our model equation then is A of t is equal to A naught. Oh, sorry, actually in this problem they told us A naught, didn't they? So we're going to change that to 100. E to the, and then K is the natural log of a half over 24,100 times T. So basically our equation needs to be in terms of t, and t over here needs to be our only variable. Then we can use that equation to answer the question. So it says, how long would it take until there is less than 0.01 grams left of the plutonium? So in other words, the A amount at time t is now 0.01. That's equal to 100 e to the natural log. I'm going to change that to 0.5. Tired of writing all these fractions. 24,100 t. Okay, and we need to solve for t, which means that we're going to need to isolate the e first. So divide both sides by 100. 0.01 divided by 100 is 0.0001. And that's equal to e to the ln 0.5 over 24,100 t. Okay, now that the base is isolated, we'll change to log form. So the natural log of 0.0001 is equal to the ln natural log of 0.5 divided by 24,100. There it is, 100 times t. Okay, and so to solve for t, just divide both sides by this. So t is equal to ln 0.0001 divided by all this, natural log 0.5 divided by 24,100. Okay, so we're going to want to type that into our calculator. And we get about, we've typed it in several times, so I'll just give you the answer there. I think you know how to type it by now, but you should probably check. 319,803 years. I rounded there a little bit at the end, so you might have 3 or 4 or something. Okay, but it should be super, super close. So let's see if that makes sense. Okay, 24,000 is the half-life. Okay, we started with 100 grams and we only want 1/100th of a gram left. So yeah, it should be a lot of years. So that does make sense.